Hello, folks. It is 1 p.m. Eastern Time, and we're just getting live here. Let me go ahead and set up my screen share. This usually takes a moment or two. Share my desktop. And what you're going to see is what we've got going on here. Now, we're going to start with a quick little daily update because the news was preempted this morning. We're going to talk about that for the majority of the time today. What you're looking at is the southern half of the Earth-facing solar disk in 211 angstroms. I like this one because it shows coronal holes really well. Those are the dark patches. It shows filaments really well, which are the thin, dark ropes. It shows coronal mass ejections and solar flares pretty well. You can see some far side eruptions on the left side. They're going off the, just behind the southeastern limb there. There's two pretty good sized ones. There's one, and then there's another one you can see faintly. Coming up, and we'll take a look at the top of the northern Earth-facing solar disk right now. There was some more solar eruptions here as well. You can see in the last 48 hours, there was one that just actually left at the beginning of the last 48-hour period. You can take a look at my cursor. We can see a plasma filament up here. I know that's a dark patch, but there's a little rope in the middle if you look in closely. This is a coronal hole, and so is this. This one actually has a filament, and you can actually see a filament coming over the northeastern limb here. Figured today was a pretty good day to do the announcement on the sun and earthquakes. Look at that filament. Sorry. Gotta love the beauty of those things. They can be hundreds of thousands of kilometers long and can erupt without a solar flare warning and produce just as large as CMEs. But anyway, we thought it was a pretty good day to give our announcement on the sun triggering earthquakes because everything is fairly calm right now. Apart from these far side solar eruptions, there's not much going on. The solar wind is fairly calm, and let's go ahead and pull up space weather news. This is spaceweathernews.com. This is the free resource that we've made for you guys today, that we made for you guys in the past couple of weeks here. And checking in today, we can see solar flaring. That's the GOES X-ray flux right here. Very low, or not even cracking up into C range. Coming down to the solar wind, which is right here, and I'll actually click this so we can zoom in, get a little closer. You can see that solar wind speed in yellow is still above average, as it is right around 500 kilometers per second, but it is waning back down now after having been fast due to a previous coronal hole that was facing Earth. These density spikes you see right here, this is just a product of the solar wind speed slowing down. The particles are slowing down, they're bunching up, they're grouping together, and that's why you see their higher readings. Where you see the more sustained readings down below it, that's what the solar wind is really doing. And these slight little jolts up here, while they're real readings, they're not really going to be affecting our magnetosphere much. We're going to come back really quickly to 211 angstroms, and I'm going to zoom out a bit so we can take a look at the full extent of the current coronal hole. This is a lot further south than I really had anticipated it going. This is all part of the same northern positive coronal hole. Let's actually pull that up really quickly here. No point in me just explaining it when I can show it. Forgive me, it'll be just a moment or two until we're all watching this. Okay, so as you can see, what's departing over here on the right is all red. That's all part of the southern negative coronal hole. And what we have here is the northern positive coronal opening right here. And yeah, I guess it does sort of dip down below the equator there, although it's not very strong at that point. The majority of the opening appears to still be about a day or so away, and that is important because we have had about a week of very, very low seismic activity. It was essentially 6 or 7 days ago that we had, it was 8 days ago that we had the 6.9 in Alaska, and we had the 7.0 in Indonesia. That's when that other coronal hole was facing Earth and the planets were lining up. Well, the planets are lining up again now, as we've been seeing in the morning news. We have Venus, Jupiter, Mercury, all kind of coming together there for a quasi four-way alignment, we'll call it. And at the same time, we have these coronal holes that are set to face Earth. And so not predicting any large magnitude, say 7 or higher, but we haven't seen a 6 magnitude quake in days, and seismicity as a whole has been lessened over the last week. But with the planets lining back up again over the next couple of days and this coronal hole facing Earth, and in addition to that, the as Kong Pop would say, the longitudinal wave influence of these far side CMEs, which will reach 1 AU away from our star in about another day and a half to 2 days, those will also create effects at Earth. So at this time, we are sort of at the end of this quieter period, at least on Earth. No real reason to think that the sun's going to fire up anytime soon, but while the quiet on the sun probably will continue, the quiet seismicity on planet Earth is likely to change in the next couple of days. That's pretty much your update right now. Let's go ahead and talk about the sun and earthquakes. I'm zoomed in on my videos list here on YouTube. You can see these are all the morning news from the past couple of days. But this morning, if you were around and you were watching, you know that there was no morning news. And that is because we were talking about how the sun triggers earthquakes. And as of this morning, we have officially self-published on spaceweathernews.com the manuscript that I've been working on now for a very, very long time with Dr. Kong Papu Yen and Dr. Chris Holloman. Let's go ahead and go right to that page. If you watch this, a lot of people I see, by the way, you guys are sharing this and I love it. When you share it, if we can share the page that has everything on it, that would really be helpful. So if we go to spaceweathernews.com, and then it's literally just -SPF. I don't know if you guys can see my URL bar, but this is spaceweathernews.com and then /SPF for solar polar fields, like that. But anyway, on this page, you can find an open letter to seismologists, geophysicists, etc., explaining how we got here, what we're doing, and why they should take a look at the manuscript, which is right next to it. By the way, these are all free and open source. Anyone can download it. Anyone can read it. Anyone can write an article about it. We are very, very available for interviews, by the way. This is the manuscript. Love to get reviews on that. It will be very helpful to have what the industry would consider qualified reviews from geologists or seismologists or astrophysicists or space weather scientists. But personally, I value the feedback of everybody. And so chances are, if you're listening to this, you've got a half a brain at least in the first place. So if you'd like to take a crack at reading the manuscript, and whether or not you're going to be able to understand Appendix A depends on how well you understand math. I'm actually still wrapping my head around some of the formulas we use, but I at least understand where they came from and how our factors that we're looking for really are indeed embodied in the algorithm. And so, yeah, we have Appendix A right here, and we have Appendix B. Appendix C is in the reference material, and there's a link to it as well. This is the video from this morning, so that you actually don't have to send people to the YouTube video. The YouTube video is actually right there on the page as a supplemental. All questions, inquiries, and comments, reviews, whatever, ben@observatoryproject.com is my email. These are all resources for you guys. I know a lot of you guys operate blogs and other things like that. If you want to write something about this, you feel free to use any of these images, or go ahead and screenshot something, or anything else you see from the actual paper. Just, of course, credit where you got it. We want this to be disseminated, and I want you guys to feel free to use as much of the stuff as possible. Anyway, that was kind of the boring stuff. Let's get into exactly what's going on here. And I'm going to go ahead and pull up the solar polar fields data. This is kept by Stanford University, the Wilcox Solar Observatory. And what they're doing is they're measuring the northern polar fields and they're measuring the southern polar fields. If I can just go back to this for a second. You know, we have polar fields that come out of the north, polar fields that come out of the south, just like we have on Earth. They wrap around to create the magnetosphere here at our planet. These help form the heliosphere on our sun. And so the blue is the northern fields and the red is the southern fields. Now, a lot of people know that at sunspot maximum, the poles reverse on the sun. Well, here we actually see that embodied about every 11 years. Now, while this cycle is perfectly in sync with the sunspot cycle, it's very inverse. If you think about it, at a polar reversal, when something is changing from positive to negative or negative to positive, there's really not much magnetism going on at that point. You're very close to crossing zero, and that's what we see here, we see here, and we see that here. And we are basically just coming out of another one right now. These are the times when sunspot levels are high, solar flaring is high, CMEs and geomagnetic activity and solar particle flux is high. But these are the times of polar minimum on our star, when the polar fields are weakest. However, during sunspot minimum, when there aren't a lot of sunspots, flares, CMEs, etc., this is when we are at polar maximum, when the polar fields of the sun are at their strongest. So just a little something interesting there. This green line you see running down the middle is the average fields, and essentially that is just adding the north and the southern magnetism to see which is sort of winning at Earth, I suppose you could say. So for example, right here, you can take a look at this field and say, okay, the north is positive here, the south is negative. Well, which one is more effective at Earth? Well, above the line here, the north is more effective. Below the line here, the south is more effective. So you can see this is really about what is Earth feeling from all of these things. And essentially, what I meant when I said that the algorithm is complex, but it's really communicating simple ideas, is this. We're looking for the peaks in magnetism. So basically, the extreme points, these peaks right here that we see on a shorter time scale. You clearly see the 11-year sunspot cycle, and then we have the shorter 1-year oscillations. Well, the peaks in magnetism for those 1-year oscillations, that is one factor that we look at. Another factor that we look at is a pole reversal, because technically going from positive to negative or negative to positive is the moment when a pole becomes a push or a push becomes a pull. And so when you have either of the northern fields or the southern fields reversing polarity, or when you have the average fields reversing polarity, these are the areas that we looked at to be significant. And don't want to belabor it too much. The paper's there, and I did mention it in this morning's show, the Sun and Earthquakes. But really, this worked out a lot better than even I would have imagined. I'd like to think that when you eyeball some of these things, and let me just go ahead and pull up this. This is one of the figures from the paper, and it basically shows 6 of the largest earthquakes of the current, or basically this previous polar field cycle. And you can see how they all fall. Number 1 right here, this is actually the 9.0 disaster in Indonesia. This is right exactly, it was within 24 hours, I believe, of the average polar fields reversal. Number 2, this, I don't remember specifically where that one was. It is in the paper. You could see that is at the secondary peak of the southern positive fields here. Number 3, you can see where we are at a negative peak of the northern fields. And I know this is down at the bottom, and we're kind of trained to think that high means more, but this central line is the baseline. So this is 0, and we're moving away from 0 and positive and then negative down below. So this is another peak in magnetism right there. And then, of course, we have Chile, 8.8, 2010. Japan, 9.0, March 11, 2011. And this right here, this is something interesting, and this is something that I talk about a lot in the paper. Really looks like this hits the mark right here, doesn't it? Well, according to the algorithm we set up, just simply based on picking some average time widths around these dates, this actually falls a couple of days too late. Now, do you think that's because number 6 is unrelated to this peak in magnetism? Or do you think maybe we just aren't perfect when we made our algorithm? A big part of the manuscript you're going to find in the discussion is ways that we believe we can improve this already. Just after, even since we wrote the first draft, that section on how we could improve the manuscript is actually born over the last 2 or 3 months during the revision process with earthquake science. And so this is something where you can say, all right, well, either this is wholly unrelated, and actually, even though there's only 1 earthquake listed here, there were actually 2 magnitude 8 earthquakes on that day. This is April 11th, 2012. And the reason why it makes this list is because one of those was an 8.6 or an 8.7, depending on who you look, whose list you look at. And so that makes it one of the top 6 largest quakes of the last cycle. But anyway, so what we have here is something where it looks like, man, really? Did that just miss by less than 2 days? Well, if we take into consideration the fact that maybe that actually is tied to this polar peak right there, that extreme in magnetism, and we just need to tweak a little bit, we're starting to get to the point where no longer, and I'm going to be quoting from the paper in the morning video if you haven't heard this before, we move from containing about 79% of the massive quakes in only 40% of the days to getting closer to 90% of the earthquakes in just about 43, 44% of the days. And there are a couple other ways we can cut those days back too. It looks like we're really open to having more going on here with this. Now, just make sure everything is still rolling. Yeah, it appears everything is still rolling. We are going to go ahead and take a couple of questions. Let me go ahead and pull this other thing back up here. Okay, so you all should be seeing now my logo, which likes to pulse every time I speak, apparently. And I'm going to go ahead and read off some of the questions that we received. First of all, we got a lot of great questions when we asked for questions. However, as always, when we ask for questions, the majority of them seem to be about whatever is in people's heads that day and not on the topic of the polar fields. So we're going to just keep it to the questions about the solar polar fields today for the sake of focus. There were great questions about coronal holes and solar wind causing earthquakes that we actually address in our upcoming book, and many other questions that I just don't have an answer to. But here we go. One question that came through asks, it is known that high pressure on rock creates electric currents in those rocks and therefore also magnetic fields. Are there ideas and calculations how that effect fits into the puzzle, or is it all thought to be a one-way effect, sun to earth only? Well, there are definitely ideas about how this is working, and that's really borne out in the paper. The idea is that you have piezoelectric forces. We are looking indeed at, electric currents, static discharge, the earth as a capacitor. Essentially, that's what our manuscript talks about, the earth as a capacitor model. Now, do we have actual calculations on how that would work? No, not on the mechanism. That would be extraordinarily difficult to model, and it would probably take a supercomputer. The calculations that we have, like I said, are simple. They are merely comparing the list of 8 magnitude earthquakes with the list of solar polar fields data to see if there's a relationship of dependence. Another question, and this is a great one, asks, is sympathetic resonance frequency critical to action at a distance as it relates to Earth-Sun connections? And can these frequency oscillations be a product of man-made sources of electromagnetic radiation? Well, it's a big yes to the sympathetic resonance frequency. Very much like tuning forks. Again, in our upcoming book, that's how we pretty much describe these planetary interactions. Not much more to say about it than that, but essentially in this system, in this solar system, when one sphere sings, they will all tend to sing. And that's pretty much just how it is. I don't want to go ahead and blow the cover off everything right now, but to the second part of the question, yes, humans can mimic those EM situations, but only on a very small scale. Tesla actually built an earthquake machine, and it was, because Tesla was Tesla, he had it figured out pretty much perfectly, but he still couldn't produce a quake big enough to do any damage. And this is simply because of the fact that, we're talking about it takes the force of the earth to create most earthquakes. When it comes to these 8 magnitude earthquakes, it looks like it takes the force of the sun. Humans can have these tiny effects one way or another, but I can promise you that they're not quite caught up with our imaginations just yet. There's a question about, does the paper include planetary alignments, or is it all polar field based? I would love to get a paper going on the planetary alignments, but that would be very difficult, and so I just decided to put that in our upcoming book as well. I think you'll find the information fairly straightforward, extensive, and not overwhelming. Tried to be a succinct communicator on that one. Sick of talking about my book, actually. What 3 monitoring devices, satellite or terrestrial, would you like to see implemented to better monitor space electromagnetism? I think this is probably the favorite question that I got. Couple things I would want to see: 2 satellites and an array of ground-based stations for this. First thing we need is we got to get something like the SDO, but for Earth. And that was what we were looking at with the pink sun. That's what you guys see every day with the yellow, the red, the orange. These are all different AIA wavelengths, and we need something like that pointing at Earth, because we need to see, we need to be able to see Earth's L shells, especially since we know that, you know, the L2 shell, among others, is directly tied to earthquakes in terms of its variation just before the earthquake occurs. And so we need to be able to monitor Earth's fields a little bit better. And I was hoping that that's what Swarm was going to be doing, and some of these other things. And in a way it is, but it's doing it in a very quantitative fashion. And could you imagine if we had Swarm data about the sun, and our information about the sun's magnetic field came from, you know, calculations? Like if we were detecting numbers, you know, as data coming from the satellites looking at sunspots, as opposed to being able to see them, as opposed to being able to see the solar flare and the coronal mass ejection. When you just think about it like that, you realize we need an SDO for Earth. Next, we need a new Demeter satellite. Or if not a new one, we need the current Demeter satellite to be revived and put in the use of somebody who will actually put it to good use. Let me explain. There's a number of references in the paper to changes in total electron content or critical frequency of the ionosphere directly above the epicenter of massive earthquakes up to days before they occur. Now, how did we detect these things? Almost all of them were detected by the Demeter satellite. And the interesting thing is scientists were able to watch this happen, and then write papers about it. In fact, I cite 3 such papers in the manuscript. And this includes the Great China Earthquake of 2008, Chile 2010, Japan 2011, and Haiti 2010 as well. That one wasn't a magnitude 8 earthquake, but it was big enough to be well studied. They all had this. They all had this data, and they were looking at it, and they were able to, after the fact, write papers about it. And yet it has never once been used to create an earthquake warning. It has never once been used to attempt to save a life. And I know why that is the case. It is because they don't want to be wrong, cause panic, cause chaos, cause looting, and essentially cause more damage than potentially the earthquake could cause itself, especially if it doesn't end up happening. But still, the idea that it has to be one of those polar extremes, although you might think I'd be in favor of it, I'm not. I think we can find a middle ground where we don't cause a lot of panic. We educate the people on what we're talking about here. And then we use the Demeter data for that. The Demeter satellite issue is one of the more frustrating things that I've ever come across in these communities. I wouldn't go so far as to say it's a conspiracy, because I wouldn't want to be the person in charge of making that decision. Do we use this to predict earthquakes and risk everything that comes along with it? Especially if I knew how people would react, and I do know how people would react. It would be probably panic and chaos if they just sort of all of a sudden started tossing out earthquake warnings left and right. But I do think there's a middle ground. As to the third part of that answer, we would need something terrestrial, and something like it is already being implemented. Spoken with a number of researchers in British Columbia who are putting static sensors all up and down the coastline, and they're trying to see if they can detect these fluctuations, these electric fluctuations, before the earthquakes actually occur. And I think that they're going to have a lot of luck with it. It's the kind of thing where you'd need them all over the world, because the static is very localized to the earthquake area. And so anywhere you'd be worried about an earthquake, you need one of these things. But if you're looking at something terrestrial, I think that works. That works, so to speak. But anyway, getting back to this page right here. For those for those who haven't watched the videos yet or haven't been keeping up, and even for those who did, let me just quickly go through again what happened. We were planning on having this manuscript published by Earthquake Science, a very well-respected earthquake journal put out by Springer. And essentially, we went through a round of review. I was surprised. I'm not sure I understood peer review. I thought that these reviewers were supposed to essentially act like robots, basically pull out their red pen and keep their emotions out of it. We actually had some emotional reviewers saying that they thought this was very interesting, and one reviewer was actually giving tips on where he thought we might want, he or she, I don't know, thought we might want to head with this in the future. That happened both times we got reviews, actually. And everyone who actually commented, a commenter, not a reviewer as I call them, those who actually took the time to make comment, all acknowledged what was going on here. It's kind of hard to when you see how well everything matches up like this. And when this one is off by just 2 days, believe it or not, this is not the only circumstance where that happens either. We could be talking about an excess of 90% of the earthquakes fitting into less than 40% of the days when we're all said and done. But anyway, we submitted our final review on July 21st, and that was the deadline. It had to be submitted before July 22nd. 2 minutes after the deadline, 2 minutes after midnight at 12:02 a.m., the journal proactively unsubmitted the manuscript, and then just over 2 hours later at 2:20 a.m., obviously while we were all still asleep, we were locked out of the manuscript, and it was basically kicked out of consideration, and they decided they would not be giving it a review. I had expected some resistance on this paper, but to be perfectly honest, I really thought it was going to come in the form of a rejection or something else like that. I really didn't think that it was going to come in the form of, no, you're going to follow all the rules, and then they're going to come in the middle of the night and do that. And it could just be an error that they have made right there, and maybe my emails aren't getting through. Have to look at that as a possibility. Also the possibility that I'm naive. Anyway, yeah, so here's the manuscript. It is just over 7 pages long, with the acknowledgments afterwards. The references down at the bottom. There are a lot of references, a lot. But we have the appendices, an open letter on this page as well. And yeah, there's really not much else to say except I could really use your help in sharing this. I really could. You don't have to. You don't have to be anybody or in any position or have any degree to help with this. And if it seems like I'm kind of stuttering over myself right now, that is half my childhood speech impediment, which I'm going to be working through for the rest of my life, and half my discomfort in asking you guys for help with this. I was told that somebody without a relevant advanced degree in these specific fields could not publish a paper like this, but I gave it a shot anyway. I really don't care that much about the publication. To me, it was just an easier way for the information to be known. But if I really stop and think about it, I don't know if there is a journal in the world that has an impact factor that could match what you could all do if you really wanted to. So anyway, yeah, if I had a choice, I would have you guys share spaceweathernews.com/SPF, or just download the material there yourself and share it. We're available for interviews, and if you do have any further questions on this, or if you've read the paper and you have a review, or you have any comments whatsoever, please send them to ben@observatoryproject.com. Really appreciate everyone's support. over the last more than 19 months now. I still very much remember January 1, 2014 in the morning news when we first sort of floated this idea out there. It's been a long time coming, but somehow it doesn't quite feel final just yet, and hopefully with your help it won't be. Anyway, earthquake watch is starting. The sun is still calm, probably going to remain calm for a little bit longer, but we do not expect the earth to remain this calm seismically in the coming days. So I will see you guys in the morning. It is now 1:30 p.m. Eastern time. That was the news. Eyes open. No fear. Be safe, everyone.